spontaneous heating of coal. So this spontaneous heating of coal is a subject which is of very important for the mining engineers, because lot of coal is getting burned every year because of the spontaneous heating of coal. Okay, so that is why we have to see what is the reason behind the spontaneous heating of coal. So in this table, a set of elements of mining conditions which influence the spontaneous combustion of coal is given by Professor S.P. Banerjee in the year 1985. So the mining parameter conditions like category of coal, chemical nature of the coal, chemical nature of the coal, okay, and set elements uh, like some coal are highly susceptible to fire, some are poorly susceptible to fire. Okay, so so category of coal and chemical nature of the coal. There are some coal who are highly susceptible. There are some coals which are poorly susceptible. So the probability of spontaneous risk of fire is high, and the probability of spontaneous heating of coal is low. So highly susceptible coals are high risk, poorly susceptible coals are low risk. Then friability of coal. Friability of coal means your uh, friability of coal means how freely means your the coal particles, how they are freely movable from one place to other place. Friability of coal, highly friable, there is high risk is there. Poorly friable, low risk is there. And method of working. If you are working board and pillar method of mining, there is high risk. If you are working longwall method of mining, there is low risk. State of stowing, whether you are stowing the underground mines or not. Extraction with caving, if you are extracting with caving, there is high risk is there. There is high risk is there. And if you are uh, stowing, if you are not stowing, you are means with stowing, low risk is there. Extraction with caving, high risk is there. Then seam thickness. If the thickness of the seam is more than 5 meter, high risk of fire is there. If the thickness of the coal seam is less than 4 meter, it is low risk fire is there. And state of extraction. If you are going for partial extraction, so there is high risk is there. If you are going for complete extraction, there is low risk is there. The nature of extraction. Extraction with more than one slice. Extraction with more than one slice, there is high risk. If you are working one slice only, there is low risk. Then geological disturbances. If geological disturbances are present, there is high risk of fire. If geological disturbances are absent, low risk of fire is there. Then rock bombs. Rock bombs, if it is present, there is high risk of fire. And if rock bombs are absent, there is low risk of fire. Then geological dikes. Dikes. If dikes are present, high risk of fire is there. If dikes are absent, low risk of fire is there. Low risk of fire is there. Okay. So dikes. Then overburden. If the overburden is greater than 300 meter, high risk is there. If overburden is less than 300 meter, there is low risk of fire. Then parting. If a cell structure, if the parting is cell structure, there is high risk of fire is there. If the parting is rocky and consolidated material, there is low risk of fire. Then state of consolidation of barrier. State of consolidation of barrier pillar. If the barrier pillar is fractured and crossed, then high risk of fire is there. If the barrier pillar is well consolidated, low risk of fire is there. Then scope of accumulation of fines. Scope of accumulation of fines. If there is fine accumulation, high risk of fire is there. If fines are avoided, low risk of fire is there. Then your method of ventilation. Method of ventilation. Advancing type of ventilation, there is high risk of fire. Retreating type of ventilation, low risk of fire. Then quantity of ventilation. Quantity of ventilation. Intensity of pressure difference high, then high risk of fire is there. Intensity of uh, pressure difference low, then low risk of fire will be there. Then humidity of the mine. Humidity of the mine. Humidity of the mine. So in wet mines, there is high risk of fire. In dry mines, there is low risk of fire. So humidity also plays an important role for the fire to take place in underground coal mines. So if the mine is wet, then high risk of fire is there. If the mine is dry, low risk fire is there. And source of hot spots. Source of hot spots. If hot spots are present, if hot spots are present, if hot spots are present, high risk of fire is there. If hot spots are absent, low risk of fire is there. Gas emission rate. If gas emission rate is low, there is high risk of fire. If gas emission rate is high, low risk of fire. And size of panel of the face. If you are working with large size of panel of face, there is high risk of fire. If you are working with small panel size, there is low risk of fire. Then rate of phase advance. If the rate of phase advance is slow, high risk of fire is there. If the rate of phase advance is fast, low risk of fire is there. Then chances for blockage of phase advance. If the chances for blockage of phase advance is present, then there is high risk of fire. If chances for blockage of phase advance is absent, there is low risk of fire. So these are some of the parameters which affect the spontaneous heating of coal. So let us discuss now what are the stages of spontaneous combustion. What are the different stages of spontaneous combustion of coal? So once one recognizes uh, three stages of spontaneous combustion of coal in coal mines. There are three stages of spontaneous combustion of coal in coal mines. One is incubation period. Incubation period. then indication period, then open fire. There are three stages will be there. One is incubation period, one is indication period, then third one is open fire. Then only you will get the open fire, third stage. So the first stage is the incubation period. So what is incubation period? It is the period between the onset of fire, fast oxidation. It is the period between the onset of fast oxidation and the time point when one can detect by the senses. It is the period between the onset of fast oxidation and the time point when one can detect by the senses. Incubation period. In a broader sense, it denotes the period between the beginning of coal extraction in a district or panel and the appearance of first signs of heating. Appearance of first signs of heating. So that is why the incubation period is very important period. So during incubation period, one does not detect heating during one's passage through mine workings. So the incubation period varies widely depending on characteristics of the coal, seam thickness, nature of the immediate roof, method of working, and method of roof control, irregularity and continuity of working, air leakage, and heat accumulation in the environment. So these are the factors which determine the incubation period of coal. For low rank coals, the incubation period generally varies between 3 and 6 months. For low rank coals, poor grade coals, the incubation period generally varies between 3 and 6 months. With high rank coals, it varies between 9 to 18 months. Under adverse conditions, the period can be less than 2 weeks, especially with low rank coals. So if the incubation period is 2 weeks, less than 2 weeks, it is very dangerous because the coal will catch fire very quickly. Then what is indication period? The end of the incubation period is the beginning of the indication period. It is marked by sweating and haze, which is caused by the warmed up air from a fire area cooling and coming in contact with the cooler coal, rock, and metallic surfaces and depositing moisture. So the indication period is often of very small duration, lasting sometimes only a few hours and end with the appearance of the fire stink. The fire stink can be easily recognized by its characteristic petrolic smell. So if there is a fire stink is there, so the smell of petrol will come out. The smell of petrol uh, will come out, from which you can know there is fire. There is fire. So the third stage is the open fire. Third stage is the open fires. After the two stages are passed, then third stage will come. Open fire will be there. Open fire will be there. So after the indication period, open fire with visible active combustion breaks out. In open fires, seams seldom burn with a bright flame, but the glow developing bluish white clouds of smoke. Then how to detect spontaneous combustion? Whether there is spontaneous heating or not, how to detect? Detection of spontaneous heating of coal. Spontaneous combustion of coal. Okay. So the detection of spontaneous combustion in its early stage is very much essential for its prevention. Earlier, a fire detected, easier it would be to deal with. If you detect the fire very early, then you can deal with it. Spontaneous combustion of coal in mine workings may be detected by physical means or by chemical indications given by the heating itself. So there are three classes of detection of spontaneous heating of coal. How to detect the spontaneous heating of coal? There are three classes of detection. First one is early detection of physical symptoms through the human senses. Conducting thermal survey using thermal devices. Monitoring gas concentrations in return airways and sealed off areas, and making compositional analysis of mine environment. So there are three classes of detection of spontaneous heating of coal. One is early detection of physical symptoms through the human senses. Second, conducting thermal survey using thermal devices. Third, monitoring gas concentrations in return airways and sealed off areas, and making compositional analysis of mine environment. So the early detection, first one is early detection of physical symptoms through the human senses. So this is the oldest technique. Reliance has been placed on these indications in the past for early detection of spontaneous heating. Development of heating in a group is generally accompanied by the appearance of haze, sweating of the strata, gob stink or fire sting, sound, smoke, and fire. So these are the indications of fire detected by human senses. These physical symptoms of heating can be identified through human senses. Then what is gob stink? What is gob stink? Usually, the first indication of a heating that can be detected by the human senses is the characteristic odor of the gob stink in the air coming from the suspected area. This tarry smell, this gob stink is tar-like smell, tarry smell, sometimes described as petrolic smell or aromatic smell, termed as gob stink or fire stink. So gob stink or fire stink smells like a petrol. It is considered as a sure warning to the initiation of spontaneous heating of coal since the earliest times. In the initial stages of heating, the smell resembles that of petrol, but as the heating progresses, it changes to kerosene and later to a tarry odor. A strong smell indicates that the heating has made sufficient headway. The smell is caused by distillation gases like saturated hydrocarbons and higher hydrocarbons produced during the oxidation phases. The characteristic smell normally found in a coal fire area once experienced can never be forgotten and cannot be missed. Then second type of indication is hazy atmosphere. In the initial stage of heating, as the moisture released from coal come in contact with cooler ventilating air and thereby condense, making haze-like formation, making haze-like formation. Okay. So what is haze? Haze in the initial stage of heating As the moisture released from coal come in contact with the cooler ventilating air and thereby condense, making haze-like formation. So haze is visible a little away from the seat of fire, that is near the intake side of the ventilation. Typical signs of haze are poor visibility of the mine environment in the vicinity of heating. In the vicinity of heating. Okay. Then what is sweating of the strata? Sweating of the strata. This is the third indication of fire. This symptom is observed at an advanced stage after formation of haze, caused due to condensation of water vapor released from coal due to spontaneous heating and formation of water droplets on the roofs, on the walls, on the timber supports, or any other cooler surfaces in its vicinity. In its vicinity. Okay. So the uh, um, fourth indication of fire is sound. Sound. At times, typical creaking sound from collapse of strata or due to crack formation in them may be heard behind the stopping or barriers, which could be indicative of advancement of fire. Sometimes increased activity and chirping of cockroaches and crickets, possibly caused by increase in temperature, may be considered as warning of the advancement of the fire. Then smoke in airways. So wherever there is fire, there will be smoke. So smoke can only be observed above the ignition temperature of coal when fire has set in. When fire has set in. So these are the human senses. Right? You can come to know if there is a fire from the human sense. But there are some limitations of detection of fire by human sense. Haze or sweating of the strata may give misleading information, giving false alarm at places where there are chances for the humid return air to meet the comparatively cooler intake air. Sometimes the haze or sweating will give misinformation. For this reason, haze formation or sweating of strata are taken more seriously in dry mines and with coals of lower moisture content, less than 5%. The early physical symptoms. The early physical symptoms may be totally missed, even in dry mines, depending on the mine environment and the rate of progress of heating. Even today, ghosting is considered a very useful warning for recognizing the onset of incipient heating or the advancement of fire in coal mines. But physical symptoms like ghosting also cannot detect heating at a very early stage, at least not up to 120 degrees centigrade or so. One cannot access the degree of heating from smell alone, which demands measuring quantitative changes that occur during the heating of the coal. Therefore, we have to conduct thermal survey to um, make sure that there is spontaneous heating of coal. So you have second type of detection is conducting thermal survey using thermal devices to measure the temperature of the strata. So the second class of detectors are thermal devices used to determine increase in temperature. Infrared scans of roadway sites employed to identify the emission points of warm gases into airways and are useful for localized heatings in pillars or around stoppings. So thermocouples or thermistors left in GOB areas, however, they too have met with very little success to the present time with following demerits. Even the thermal devices are having some demerits, limitations. First, their wearing is unlikely to withstand the mechanical stresses of an active cabin zone even when seized. Secondly, the thermal conductivity of crossed rod is low. Hence, the temperature, even within a meter of an active center of heating, may indicate no abnormal condition. Therefore, there is a third way of detecting the fire: monitoring gas concentrations in return airways and sealed off areas and their trend analysis. How to monitor? Monitoring the quality of air in a mine is the modern, most widespread, and dominant method of detecting spontaneous heating of coal. This method of early detection is based on monitoring gas concentrations in return airways and analyzing the changes in air composition. Sampling the air downstream from a fire or from within a newly sealed off area and plotting the trends is the primary method of tracking the behavior of the fire. As the gases emitted vary with the phases of oxidation, time and temperature, it is necessary to employ skilled interpretation of those trends. So, for this monitoring gas concentration, there are certain type of indices are used. Fire indices, susceptibility indices of spontaneous combustion of coal. So, based on the compositional analysis of mine environment, a number of ratios or fire indices have been suggested to detect not only the onset of heating in mines, but the degree of it as well. So they assist in the interpretation of fire gases. Some of these gas ratios or indices used in interpreting trends of gas concentrations produced by mine fires are given below. Carbon monoxide divided by oxygen absorbed, which is called the Graham's ratio or index for carbon monoxide. Index for carbon monoxide. Carbon monoxide divided by oxygen absorbed. So that is called your Graham's ratio or index for carbon monoxide. Similarly, carbon dioxide produced divided by oxygen absorbed is called your Young's ratio. Graham's ratio is carbon monoxide. Young's ratio is carbon dioxide. Then there is another ratio is there which is called Willet's ratio. Carbon monoxide divided by excess nitrogen plus carbon dioxide plus combustibles combined together. This ratio is called a Willet's ratio. Then another type of ratio is there which is called Jones and Trickett ratio. Jones and Trickett ratio. So what is Jones and Trickett's ratio? It is carbon dioxide plus 0.75 carbon monoxide minus 0.25 hydrogen divided by oxygen absorbed. That ratio is called Jones and Trickett ratio. Then another ratio is there, carbon monoxide divided by carbon dioxide. This is called oxides of carbon ratio. So these are the different type of ratios used for monitoring the coal mine fire. Graham's ratio, Young's ratio, Willett ratio, Jones and Trickett ratio, oxides of carbon ratio. So a feature of several of the ratios is the oxygen deficiency. Oxygen deficiency, delta O2. So this is a measure of oxygen that has been consumed and is based on two assumptions. First, that the air has been supplied with 20.93% oxygen, 79.04% inert gases, excepting 0.03% carbon monoxide. That 79.04% contains traces of other gases, but is referred to simply as nitrogen. Secondly, it is assumed that no nitrogen has been consumed or added except from the air through the air under consideration. If no oxygen is consumed, then the oxygen by nitrogen ratio would remain at 20.93 divided by 79.04, which is equal to 0.2648 or 0.265, irrespective of the addition of other gases. For any measured values of oxygen and nitrogen, the concentration of oxygen that was originally in place can be calculated as 20.93 divided by 79.04 into nitrogen. That will give the concentration of oxygen. So hence, the amount of oxygen that has been consumed or oxygen deficiency is given as delta oxygen delta O2 is equal to 0.265 divided by oxygen percent. So on the basis of that, you calculate the Graham's ratio. It is the most widely used indicator of an incipient heating in coal mines and has often given warnings several weeks before any odor could be detected. It is recognized that coal, on being exposed to air, even at room temperature, consumes oxygen and gives rise to gases like carbon monoxide and carbon dioxide as oxidation products. As carbon dioxide may be produced from other sources or may be lost in air due to sorption by coal or by solution in water, carbon monoxide is the most reliable indicator of heating. By 1914, Ivan Graham recognized the importance of carbon monoxide as an early indicator of spontaneous heating of coal and the equally vital influence of oxygen that was consumed. He first suggested the index carbon monoxide divided by oxygen deficiency, now known as Graham's ratio or Graham's index or the index for carbon monoxide. It has the significant advantage that it is almost independent of dilution by leakage of air, as this affects both numerator and denominator equally. Like other indices, a normal range of Graham's ratio should be established for any given mine. This will usually be less than 0.5%. Any consistently rising values in excess of 0.5% is indicative of spontaneous heating of coal. So the typical values of carbon monoxide divided by oxygen deficiency ratio for underground coal mines are given below. If the ratio is 0.4% or less, it is a normal value. If the ratio is 0.5%, necessary for thorough checkup, If the value is 1%, heating is almost certain. If the value is 2%, heating is serious with or without the presence of active fire. If the value is 3%, active fire surely exists. So from this Graham's ratio, you can know whether there is a fire or not. But there are some drawbacks of Graham's ratio. Its accuracy becomes suspect if very little oxygen has been consumed. That is, Graham's ratio is unreliable if the oxygen deficiency is less than 0.3%. This is a weakness shared by the other indices that involve oxygen deficiency. It is affected by sources of carbon monoxide other than the fire. The use of diesel equipment also sometimes they produce carbon monoxide. If the air supplied to the fire is not fresh, it occurs if the fire is fed by air that has migrated through cold workings and contains black damp, oxygenated air. Then there is another ratio which is called a Young's ratio. Young's ratio. Carbon dioxide is the most prolific of the gases. Young's ratio. Another ratio is there which is called a Young's ratio. So carbon dioxide. Young's ratio takes care of carbon dioxide. So the carbon dioxide is the most prolific of the gases produced in mine fires. Hence, the values of carbon monoxide divided by oxygen deficiency will be much higher than carbon monoxide divided by oxygen deficiency. As a fire progresses, smoldering to open flame, the burning of carbon monoxide will produce an increase in carbon dioxide. Hence, a simultaneous rise in carbon dioxide by oxygen deficiency and fall in carbon monoxide by oxygen deficiency indicates further development of the fire. However, as both ratios have the same denominator, the straightforward plots of carbon monoxide and carbon dioxide show the same trends. Young's ratio is nearly independent of dilution of fresh air. It suffers from similar limitations to Graham's ratio. Additionally, the concentration of carbon dioxide may have been influenced by adsorption, its solubility in water, strata emissions of the gas, and other chemical reactions. Thus, the extraneous origin of carbon dioxide as well as its solubility in water make the interpretation anomalous at times. Then there is a third type of ratio which is called a Willet's ratio. Willet's ratio. This ratio was introduced by Dr. H.L. Willet in the year 1951 with specific reference to situations where there is a higher than usual evolution of carbon monoxide by ongoing low temperature oxidation. In these cases, gradual extinction of a fire in a sealed area may not be reflected well by the carbon monoxide trend alone, but as a percentage of the air-free content of the sample. In these cases, Willett suggested to use the ratio carbon monoxide produced divided by black damp plus combustible gas So besides the analysis of carbon monoxide to understand the magnitude and extent of fire, This ratio can be used only as a supplementary index along with other higher indices. So there is another ratio which is called Jones and Trickett ratio. There is another ratio which is called Jones and Trickett ratio. Jones and Trickett ratio, JTR. Jones Trickett ratio is used as a measure of reliability of sample analysis and also as an indicator of the type of fuel involved. It can be used for the gaseous products of both fires and explosions. Jones and Trickett ratio, JTR, giving the relationship between the products of combustion with oxygen deficiency, is defined as below. This is called your Jones and Trickett ratio. Carbon dioxide plus 0.75 carbon monoxide minus 0.25 hydrogen divided by oxygen deficiency. That ratio is called Jones and Trickett ratio. Dilution by fresh air has no effect on the Jones-Trickett ratio. However, it is subjected to the limitations of oxygen deficiency. This ratio helps in distinguishing coal dust explosions from methane explosion from examination of post-explosion gases. Like if the JTR value is less than 0.5, it indicates methane explosion. If the JTR value is around 0.85 plus or minus 0.18, it indicates coal dust explosion. If the JTR values in between are indicative of both methane and coal dust explosion. Then another ratio is there which is called oxides of carbon. Oxides of carbon ratio means carbon monoxide divided by carbon dioxide. This ratio is called oxides of carbon. The oxides of carbon ratio, carbon monoxide divided by carbon dioxide, or the ratio of POC, products of combustion, is a useful pointer to the progression of fire, rising during the early stages and tending to remain constant during flaming combustion. However, the carbon monoxide by carbon dioxide rises rapidly again as a fire becomes fuel rich and is an excellent indicator of this condition. This ratio may also be favored because it is unaffected by inflows of air, methane, or injected nitrogen. It is, however, subject to variations in carbon monoxide and carbon dioxide that are not caused by the fire. Then another ratio is there which is called C by H ratio. C by H ratio. Okay, C by H ratio. The C by H ratio of the mine gases was introduced by Ghosh and Banerjee, Professor A.K. Ghosh and Professor S.P. Banerjee in the year 1967 for assessing the intensity of fire along with oxygen consumption values that indicate extensity character of it. They argued that in case of burning of fuel, mainly compound of carbon and hydrogen in varied proportion, the temperature determines the extent to which the carbon and hydrogen part of it would burn. At low temperature, the hydrogen part may burn completely, but there would be a lot of unburned carbon deposited as soot. In case of rapid burning, methane, in case of rapid burning of methane, the C by H ratio calculated from the product gases is always less than 3, which is the maximum value for complete combustion of methane. Likewise, the maximum attainable C by H value for complete burning of bituminous coal lies between 16 to 20, depending on the type of the coal mined. Higher C by H values indicate burning of cellulose bodies, timber, etc., having higher C by H values, uh, while lower values indicate partial burning of coal. Thus, the degree, thus the degree of or intensity of burning of coal are judged from the value of C by H ratio of the product gases obtained. So how to prevent spontaneous combustion of coal? Prevention of spontaneous combustion is based on two factors: elimination of coal from the area, control of ventilation. There are two methods by which you can prevent the spontaneous combustion of coal. So control of ventilation, to exclude oxygen entirely from the area, to supply a sufficient flow of air to dissipate the heat efficiently as it is generated and before a critical temperature is reached. Several methods and strategies which can be adopted to prevent and control spontaneous combustion of coal, which are given below. Mining layout. Proper mine layout design is very important for prevention of spontaneous heating of coal. Design of general mine layout should be simple so that each area section can be quickly and effectively sealed up or isolated at short notice without affecting production in other districts. Panel system of working appropriate for mining seams liable to spontaneous heating of coal, which facilitates effective sealing with a few stoppings. The panels must be laid as to minimize severe crossing of coal during extraction. Size of each panel should be based on incubation period of coal and rate of extraction. Panels must be of a size which would permit complete extraction within the incubation period of the coal. The size of the panel barriers needs to be sufficient for stability purpose. Panels with independent ventilation should be formed. When working seams by board and pillar method, the size and shape of the pillars must be sufficient to avoid excessive crossing at edges and corners. Side bolts can be used and low viscosity grouts may be injected to maintain the integrity of the pillars. In case of longwall mining, face lengths smaller than 60 to 65 meter should not be made to ensure good closure and compaction of the coal. So then these things, coal winning, other things we'll discuss in the next class. So today we have discussed about the various factors which are responsible for spontaneous heating of coal, and we have also discussed the various stages of spontaneous heating of coal and how to detect detection of spontaneous heating of coal. There are three methods of detection of spontaneous heating of coal. One is by human sense, second one is by thermal survey, and third one by gas survey. So these are the uh, three methods available for detection of spontaneous heating of coal. Different gas ratios also we have discussed, Graham's ratio and other uh, ratios we have discussed. So this is all about today's class. Thank you. Have a good day. Thank you.